Hello everyone, I am Ankita Kulkarni. I am presenting on topic concurrent computing, which is a third module. To begin with, first we'll see about thread programming. Throughput computing focuses on delivering high volumes of computation in the form of transaction. Initially related to the fields of transaction processing, throughput computing has since been extended beyond that domain. Advances in hardware technologies led to the creation of multi-core systems which have made possible the delivery of high throughput computation even in a single computer system. In this case, throughput computing is realized by means of multiprocessing and multithreading. Multiprocessing is the execution of multiple programs in a single machine, whereas multithreading relates to the possibility of multiple instruction streams within the same program. Next, we'll see about introducing parallelism for single machine computation. In particular, multiprocessing, which is the use of multiple processing units within a single machine, has gained a good deal of interest and gave birth to several parallel architecture. Asymmetric multiprocessing involves the concurrent use of different processing units that are specialized to perform different functions. Symmetric multiprocessing feature the use of similar or identical processing units to share the computation load. Other examples are non-uniform memory access, that is NUMA, and clustered multiprocessing, which respectively define a specific architecture for accessing a shared memory between processor and the use of multiple computers joined together as a single virtual machine. Symmetric and asymmetric multiprocessing are the techniques used to increase the performance of commodity computer hardware. The introduction of graphical processing units GPUs, which 171R defects processor, is an application of asymmetric processing, whereas multi-core technology is the latest evolution of symmetric multiprocessing. Multiprocessor and especially multi-core technologies are now of fundamental importance because of the physical constraint imposed on frequency scaling, one which has been the common practice for performance gain in recent years. Moving ahead, we'll see about the working of multi-core processor. Multi-core systems are composed of a single processor that feature multiple processing cores that share the memory. Each core has generally its own L1 cache, and L2 cache is common to all the cores, which is represented in this figure, which connect to it by means of shared bus as depicted in the figure. Dual and quad core configuration are quite popular nowadays and constitute the standard hardware configuration for commodity computers. Architectures with multi-core are also available but are not designed for the commodity market. These have been useful technologies has been used not only as a support for processor design but also in other devices such as GPUs and network devices, which helps in enhancing and improving the performance. Next, thread APIs. So the given figure which provides an overview of the relation between threads and processor and a simplified relationship of the runtime execution of the multi-threaded application. A running program is identified by a process which contains at least one thread, also called the main thread. Such a thread is implicitly created by the compiler or the runtime environment executing the program. This thread is likely to last for the entire lifetime of the process and be the origin of other threads. Next, each of them has its own local storage and a sequence of created during the process lifetime. Each of them has its own local storage and a sequence of instructions to execute, and they all share the memory space allocated for the entire process. The execution of process is considered terminated when all the threads are completed. So the entire thread APIs and process functions are depicted in this given figure. Next, we'll see about POSIX threads and threading supports in languages like Java and .NET. First is Portable Operating System Interface for Unix is a set of standards related to the application programming interface for a portable development of application over the Unix operating system flavors. Standard POSIX 1.c version address the implementation of thread and the functionalities that should be available for application program to develop portable multi-threaded applications. The standard addressed the Unix-based operating system, but an implementation of the same specification has been provided for Windows-based system. The POSIX standard defines the following operation that are the creation of thread with attributes, termination of a thread, and waiting for thread completion, which is a join operation. Next, languages such as Java and C# provide a rich set of functionalities for multi-threaded programming by using an object-oriented approach. Since both Java and .NET execute code on the top of virtual machine, the APIs exposed by the libraries refer to managed or local threads. These are mapped to physical threads by the runtime environment in which the program develops with these language execute. Next, exposing the common operation performed on threads are start, stop, suspend, resume, abort, sleep, join, and interrupt. Moving ahead, we'll see what are the techniques for parallel computation with threads. Developing parallel application requires an understanding of the problem and its logical structure. Understanding the dependencies and the correlation of tasks within an application is fundamental to designing the right program structure and to introducing parallelism where appropriate. Decomposition is a useful technique that aids in understanding whether a problem is divided into components or tasks that can be executed concurrently. If such decomposition is possible, it also provides a starting point for a parallel implementation since it allows the breaking down into independent units of work that can be executed concurrently with the support provided by threads. So, the two main decomposition or partitioning techniques are first is domain decomposition and followed by second one is functional decomposition. First, we'll see about the domain decomposition, which is the process of identifying patterns for functionally repetitive but independent computation on data. This is the most common type of decomposition in the case of throughput computing, and it relates to the identification of repetitive calculation required for solving a problem. Embarrassingly, parallel problems constitute the easiest case for parallelization because there is no need to synchronize different threads that do not share any data. Moreover, coordination and communication between threads are minimal. So, in many cases, it is possible to devise a general structure for solving such problems, and in general, problems that can be parallelized through domain decomposition. The master-slave model is a quite common organization for this scenario, which includes the system is divided into two major code segments. One code segment contains the decomposition and coordination logic. Another code segment contains the repetitive computation to perform. A master thread executes the first code segment. As a result of the master thread execution, as many slave threads as needed are created to execute the repetitive computation. The collection of the results from each of the slave threads and an eventual composition of the final results are performed by the master thread. So the given figure, first it shows an embarrassingly parallel and second is the inherently sequential. To show how domain decomposition can be applied, it is possible to create a simple program that performs matrix multiplication using multiple threads. Matrix multiplication is a binary operation that takes two matrices and produce another matrix as a result. This is obtained as a result of the composition of the linear transformation of the original matrices. There are several techniques for performing this, but among them we are using the matrix product is the most commonly used. So the given figure which provides an overview of how a matrix product can be performed. The matrix product computes each element of the resulting matrix as a linear combination of the corresponding row and column of the first and the second input matrices respectively. So the formula for applying each of the result matrix element is given below. Here we need to follow the two conditions in order to perform a matrix product. First one is input matrices must contain values of a comparable nature for which the scalar product is defined. Second main thing, the number of columns in the first matrix must match the number of rows of the second matrix. Next, second one is functional decomposition. The figure shows the working of functional decomposition, means the different process it consists, and for each process to execute, different units of work need to be performed to get a result. In the following, in this, it shows a very simple example of how a mathematical problem can be parallelized using a functional decomposition. So let's take an example, which is to calculate the value of the following function for a given value of x, which is f of x function is equal to sin of x plus cos of x plus tan of x. It is apparent that once the value of x has been set, the three different operations can be performed independently of each other. This is an example of functional decomposition because the entire problem can be separated into three distinct operations. The program computes the sine, cos, and tangent function in three separate threads and then aggregates the result. Instead of using a data structure for keeping track of the worker thread that have been created, a function pointer is passed to each thread so that it can update the final result at the end of the computation. So that's all. Thank you.